My name is Johann. I'm from the Argonne National Laboratory. This work is a collaboration with Julie Bessac and Amanda Lenzi, both from the Argonne National Laboratory. I will talk about a way of using dense and convolutional neural networks to solve inverse problems. And this particular inverse problem involves an ordinary differential equation called FitzHugh-Nagumo. So the forward problem is the following ODE, which is described from the unknown of the membrane potential U and the recovery variable V. And there's a few constants like gamma and zeta, but also these two parameters that we're interested in the context of an inverse problem. So theta 0 and theta 1 are our inference parameters. One example solution of this ODE for a specific theta 0 and theta 1 looks like this, looks like the blue line. So the blue line is the membrane potential, and it models the spiking of a biological neuron. And this is sometimes available as data. That means given some membrane potential as observational data, we would like to find theta 0 and theta 1 in our inverse problem. So while the FitzHugh-Nagumo model is quite simple from a physiological perspective, it exhibits many of the challenges of complex neuron models like the Hodgkin and Huxley model if we consider it in an inference setting. Now let's jump to this inference setting. Let's assume we want to estimate the maximum a posteriori point. That means we want to minimize this data misfit term and this prior term. In the prior, the theta bar is the mean of the prior and sigma is the variance or covariance matrix of the prior. The data comes from the true model output for true theta and additive noise, which has also a component of correlation. So this is an autoregressive process. So if noise is added to our U theta true, one example of it is depicted here, where the orange dots are the noisy data corresponding to the clean or true membrane potential. Now, if we would plot this cost function in this minimization, it would have a very strange shape. So it's highly nonlinear, as can be seen here, where the true theta is the red X and the prior is sitting in the middle, it's the blue cross. And the covariance is chosen very widely, so the main features that we are seeing in this plot are coming from the data misfit term. And this is actually one of the problems in biological neuron-based inverse problems. The prior assumptions are actually fairly weak, and we are confronted with loss functions that are highly nonlinear. They can be non-convex, they can have sharp gradients, nonlinear dependencies, and multiple local minima. So for example, this loss function has this valley, which is the dependence between theta 0 and theta 1, and it's also nonlinear because it's having this unusual curved shape. Okay. Now, gradient-based methods would fail without very strong assumptions on where we start as an initial guess, given this cost function. Now we try to do a quite different approach. We replace the whole optimization coming from the map estimate, and instead we want to computationally learn reconstruction and inverse maps. So we want to have a deep neural network where FL are the layers of the network, L is for layers, and as the input we pass our data, so it's a time series, and the output of the network is our parameters theta. That means the map that the network is representing is essentially a pseudo-inverse of the forward operator. Now this, of course, is not directly connected to the map estimate or any other known estimates. It's its own beast, which is not quite well understood theoretically, and especially from a convergence perspective, there are still open questions. Other limitations to consider are that the architecture of the neural network, the layers, different parameters, hyperparameters, and how they are optimized. These are usually done heuristically. And another aspect is the generation of training data, which can be costly if this involves many simulations. However, it's necessary in order for this type of inference to be able to begin at all. Because without training data, obviously, you cannot train a neural network. Now, the second idea is to generate this training data. We want to use the prior that we've shown before. So thetas are represented by these Gaussian priors. That means we sample theta 0 and theta 1. And we also want to apply upper and lower bounds on them. And here's a depiction of 4 different sets of training data, which are the black dots, and a single set of the testing data, which are the blue dots. That means the blue dots from one plot to the other stay the same. It's the training data that keeps increasing and filling out the space. So to generate the training data, we need to sample, but then we also need to simulate the ODE and generate the time series output. It was the membrane potential, if you remember. So in this ODE simulation, in this case, is where the main computational cost of obtaining the training data lies. Okay, now let's see at what happens if we construct a dense neural network, and let's assume we went through a bunch of optimization steps to find a good network architecture. And you can see the steps in the paper. So I want to show 3 different cases where training and testing data of the membrane potential is noise-free, the testing data has noise, and then both of them has noise. That means what the question is, how do you train effectively given that given that you will be testing without noise, or in practice actually you will be always confronted with some noise. So this is the best case scenario, and this is more of a typical practical scenario where testing data has noise. So we see that without noise, the neural networks perform fairly well. So the spreading around the ideal dashed line is fairly narrow. This is for parameter theta 0 and this is for parameter theta 1. As noise comes into the data, the spreading becomes wider. Now, this is a dense neural network. We want to consider convolutional neural networks too to make use of the internal structure of a time series of the local dependence. So we optimized our convolutional neural network and we got these results. So the training, the noise-free training and testing looks very spot on. However, if you train without noise, the variance becomes quite wide, even wider than the dense neural network from the slide before. So in order to avoid this wide spreading, it's actually beneficial to train also with a noise model similar to what your testing data noise will be. So to compare it from the perspective of how would the CNN predictions of parameters translate to the output of the ODE, we depict the 3 cases again, and this is one ODE output, which is taken to be the median percentile of MSE. So it is something that you most likely can expect as an output from your CNN predictions when you run your ODE with those predicted parameters. So as you can see, the noise-free training when testing has noise has quite some discrepancies, and it basically supports our results from the slide before. Now I want to inspect some sensitivities of the neural network capabilities of estimating parameters. So this is one test where we were asking ourselves, is the neural network merely remembering a time series, or can it learn underlying properties or some sort of dynamics? Now, we've set up the following problem or the following scenario. For the training, we split our time series in half. So it used to be 200 milliseconds. We split it in half. That means we also double the amount of training samples. Now for the testing, however, we choose random intervals of 100 milliseconds, which lie within this time frame of 200 milliseconds. That means the exact location of the data where the signal, where the membrane potential is recorded, is not known during the training phase. So we were hoping that this can tell us if the network can understand something more fundamental in the signal than just mere remembering it and then giving prediction just based on that. So one new aspect comes into this test, which is the Fourier transform of the time series data and combination of time series data and its Fourier transform. So it's a vector of dimension 2. So these are dense neural networks, and they perform relatively poor for this partially observed time series, as you can see, for example, in the R-squared being quite far away from 1. However, the convolutional neural networks, they are fairly robust with respect to these partial observations. And as you can see, they are happy to see the time series and pretty accurately predict the parameters from this time series. So another sensitivity analysis that we have performed is how much training data is required to be able to have fairly good predictions of parameters. And as you can see, for the different cases of training and testing, noise and noise-free, our training data varies from 500 samples up to 8,000 samples. The previous results are usually shown with 1,000 samples, by the way. And this shows that already with 500 samples, so you can see the black dots, these are the 500 samples of theta, the networks can predict with a fairly high accuracy already, and you can improve the accuracy by taking more samples. We noticed something, that the convolutional neural network has trouble if it's gonna be trained noise-free, but the testing data has noise added to it. And this is outlined by the red cells. So the dense neural network seems to be more robust with respect to these training, testing, noise or noise-free discrepancies. Finally, we wanted to extend our framework in order to invert not just for the ODE parameters, but also for the parameters of the noise model. So it's the additive noise, if you remember from the beginning. Here again, I wrote down the equations. This is the ODE. Here are theta 0, theta 1, the parameters we want to infer for. And now we're adding the rho, the correlation parameter, and also the sigma, so the variance of the noise, into the inference problem. So this joint inference is actually quite rare in practice, or in the literature. So we were curious if we could make this work with our framework. That means if it were to work, then this framework would actually be quite powerful, because it can do something that's rarely achieved with other methods. So now this is the CNN only, and I want to show you two sizes of training data, and again the different data types where there's only the time series, the Fourier transform of the time series, or both as a two-dimensional vector. We see that with 1000 training samples and only the time series available, the noise parameters are basically non-predictable by the network. And the explanation for this is that the ODE operates at a vastly different time scale than this noise. That means these are the dominant signals when you add membrane potential and the noise. And so these tend to disappear when the network is optimizing. However, we can utilize our Fourier transform and time and Fourier transform in order to bump up the prediction accuracy of these noise parameters. And another alternative is to increase the data size dramatically, which also helps to increase the prediction accuracy for these other two parameters in the noise model. Well, with these results, I would like to thank you for your attention, and feel free to reach out to me and ask any further questions.